This video is a demo of the blood pressure sensor lab. It corresponds to section 20.2 of the Applied Analog Electronics textbook. Now, when we're measuring blood pressure, what is it that we're really measuring? Well, let's take a look at what's happening. When the heart beats, it squeezes the blood out of the heart and pushes it through all the arteries of your system. And what that means is you have a pressure wave. The pressure jumps up fairly quickly when the heart squeezes, and then as the heart relaxes, the pressure drops again. Heart beats, the pressure jumps way up, and then it drops again. So you get what amounts to almost a sawtooth pressure wave in your arteries. And what doctors are interested in are two values: the maximum and the minimum pressure of that repeated wave. The maximum pressure they refer to as the systolic pressure, and the minimum they refer to as the diastolic pressure. And when they're taking this measurement, they generally do it in the arm, because it's easy to get access to, at the same level as the heart, because the heart is sort of a canonical location for where to take the pressure. If you move up higher in the body, the pressure is less. If you move lower down in the body, the pressure is more. And so in order to get comparable numbers all the time, they have somewhat arbitrarily, but also somewhat naturally, taken the pressure at the level of the heart as being the blood pressure that they're interested in. And so when they're making measurements in a blood pressure cuff, they put it on the arm at the level of the heart. Okay, what is blood pressure cuff? Well, the blood pressure cuff is something that you wrap around your upper arm. Let's switch away from the paper here. It's something that you wrap around your upper arm to provide a way of squeezing your arm. And the style of cuff that you have for these cheap blood pressure meters is rather difficult to put on just one person. If you can get somebody else to help you put it on, it makes it much easier. But the idea is you want it a little tighter than I've got it here so that it doesn't flop around. And you want these arrows here. There's one labeled right arm, one labeled left arm. You want the arrow for that arm to line up with the brachial artery, which is sort of here on the inside of the biceps, on the chest side of the biceps. You want that brachial artery to be underneath that arrow. And tuck it around so there's no folds or other creases, because when you pump this thing up, it's going to squeeze your arm pretty hard. And if you've got any creases or anything underneath there, it's going to hurt. It's going to perhaps leave bruises. You also don't really want any clothing. The reason I'm wearing this t-shirt is because I can put this thing against my bare skin then. You get the most accurate pressure readings if there's no clothing in the way. If you have something like a down vest or something on, you can squeeze that pressure cuff pretty hard without actually squeezing your arm. And the result is your pressure measurements will be just way off. So don't wear a sweater, don't wear heavy clothing. Have, if possible, just put the cuff directly against your bare skin or a thin layer of lightweight material in between. Okay, this particular cuff is not one that I can use because it's been damaged. And let me take it apart here so you can see what's inside the cuff. The cuff is just basically a piece of nylon, some Velcro on it. Inside it is this plastic pouch that's sealed all the way around and has some tubes coming out of it. Sealing is done with ultrasonic welding because that's a very cheap way to seal plastic. The problem is that if you pump this thing up when it's flat like this, it makes kind of a pillow. And that pillow is pulling very hard right on that ultrasonic weld, which is a pretty weak joining method. And so what happens is if you inflate this thing when it's flat, you can tear the seam. And the reason I have a number of these dead cuffs is because that has happened in the labs. And it's happened almost always from people putting the cuff flat on the bench and inflating it. And when you do that, this thing becomes a pillow, it puts a lot of stress on that seam, and the seam sometimes tears. And then your cuff is useless. I've tried taping them shut and doing other things to try and reseal it. Nothing I've done works. I don't have an ultrasonic welder to re-weld the ultrasonic seam. Some of you might, because they're used in kitchens sometimes to seal plastic bags, but I don't happen to have one of those. So if you pop the bag, the cuff basically becomes useless. You can avoid popping the bag, though, by keeping the cuff always sort of bundled up so that it can't expand. And can't tear that seam, because if it stays like here, you can get quite a bit of pressure in it without the cuff expanding much, and so without tearing that seam. When you have it wrapped around your arm, it's not going to expand much, but you don't want to inflate it around your arm unless you're actually measuring your blood pressure, because you cut off the circulation to your arm. It's not really good for you to do that for long periods of time. Okay, I'm not going to use that cuff because that one is broken, and in fact all the cuffs of that type that I have are broken. I'm going to use a different cuff. This is one that came as part of a home blood pressure meter. I got it at a garage sale, and it's easier to put on by hand, by one person, because I just have to line up the tab here with the top of my arm, grab that part, and it's on. So it goes on right over the biceps. The tab here is such that I can still flex my elbow. You don't want it down over your elbow, you want it up on the biceps, so that when you're sitting, it's level with your heart. Okay, what else have I got here? Let's take a look at where the tubing from this one, I take it into a T-junction. One part of the T I take over to this squeeze bulb for inflating it. The other part of the T-junction I take over the pressure sensor. Now the cuffs you had two hoses, so one hose could go to the pressure sensor and one hose could go to the bulb. Here I've only got one hose coming out of here, so I have to have a T-junction. The pressure sensor is in turn connected to, here I've got a permanent amplifier board. You'll just have yours on a breadboard. And the two outputs from the amplifier, a low gain and a high gain, so after the first stage and after the second stage, are going over a TCLC running Teradek to record the pressure signal. So let's switch over to looking at that pressure signal. Okay, so here I'm running Teradek. I've got a high gain and a low gain channel. I'm sampling at 60 Hertz, and that's because if I sample at 60 Hertz, it'll alias out any 60 Hertz noise I have, and that's more than fast enough for the sort of very low speed signals that I expect to see here. So let's start recording, and now I'm going to squeeze this bulb, and as I squeeze the bulb you can see pulses there as the pressure goes up. I got it all the way to the top, and now I'm just going to let the air out, and I don't have to do anything special here to let the air out. This particular bulb has got a slow leak engineered into it. The bulbs you have don't have a slow leak engineered in. They've got a little knob that you can adjust to adjust a leak, and you need to adjust that before you start pumping it up. If you've got too fast a leak, you won't be able to see your blood pressure, because the signal will drop too fast. You won't be able to see the fluctuations that indicate that you're between systolic and diastolic pressure. If you have the leak going too slowly, you'll cut off the circulation to your arm for too long, and that's not healthy. So what I'm waiting for is for the pressure to drop back down to close to where it started. It's not going to drop all the way to ambient air pressure, but it's going to get pretty close. And once it's gotten pretty close, like about now, I can, there's a little button on here I can press to release the rest of the pressure, and then I can stop the recording. And I will save this as blood pressure 6. And now let's switch over to a GNU plot terminal and take a look at it. So I'm just going to plot it with lines. And let's take a look at what that looks like. Okay, you can see the initial pumping up of the bulb, a bunch of spikes there as the pressure went up as I squeezed, and then it dropped again, squeezed, and each time it went up a higher amount. Once I got to the top, then I just let the pressure out and it came out gradually, but you can see tiny little bumps on that. Those tiny little bumps are a result of my arm changing size slightly as the blood pulse goes through it. So each one of those is one of the pulses. And this is in fact how this style of blood pressure sensor works, is that it looks for those tiny oscillations in the pressure that are due to the pulse. It's a little bit different than the way the doctors do it in a doctor's office. There they usually have a stethoscope and listen to your arm as they pump up and release the pressure. They're doing the same thing of releasing the pressure gradually, but they are listening for sounds that occur when the blood flow becomes turbulent. And that happens when the artery is squeezed enough that it is only letting blood flow through during part of the cycle. So when the blood pressure is high, it goes through, but when the blood pressure is low, it's not going through. When the artery is squeezed like that, you get sort of pulsating flow, where it's actually stopping and starting, and you get very turbulent flow. When the pressure is very high, blood doesn't go through during any part of it. When the pressure is very low, blood flows through smoothly the whole time. So that time when it's between the systolic and the diastolic pressure, the blood makes characteristic sounds as it goes through the blood vessel, and doctors and nurses are trained to listen for that sound in order to determine when it's systolic and when it's diastolic. When the sounds start, that's the systolic pressure, and when it's dropped to when the sounds stop again, that's the diastolic pressure. That's not the way the pressure sensors we're using work. The Holmes pressure sensor doesn't listen to the sound. It's watching the pressure on the cuff itself and seeing that slight fluctuation in the pressure due to the arm's changing size from the blood flow. Okay, but it's kind of hard to read that. So what we're going to do is we're going to filter the sound, or not the sound, but the pressure here, in order to either accentuate those little fluctuations or remove them from the smooth downward flow. And that's going to be a bandpass filter to accentuate them and a low-pass filter to remove them. And I've provided a script, a Python script using the SciPy signal processing package. And the way you run it is you just say Python, and then you give the name of the script, and then a less than sign to say what you're going to read from, and that's standard in, and then a greater than sign to say what you're going to send it to. And what this is going to do is it's going to read the two columns of data. The first two columns were time and the voltage. In this case, it was the voltage of the high gain channel. It's going to read those two channels, and then it's going to put them both out again, and it's going to add two more columns. Third column will be band passed, and the fourth column will be low passed. So let's take a look at what those are. So let's go back to the GNU plot terminal, and I'm going to plot not blood pressure 6, but the output of the thing, filtered. And that doesn't look like what I called it. So what did I call it? I didn't do 6, I did 5. Let's go back and redo the filtering. Alright, so we're not doing 5, we're doing 6. And now we'll go back to the GNU plot terminal, try the plot again, and let's take a look at it. It looks exactly the same as before because we're still plotting column 2. And column 2 is the same as it was before, so there's no change here. The third column was the one that was supposed to be so if I say using 1:3, this should be the bandpass one now. So plotting that and looking at the output, and now we can see we're just seeing the fluctuations. All the slow changes, which were low frequency, have been removed by the bandpass filter, which eliminated low frequency signals. And you can see some enormous signals there at the beginning. That was the squeezing of the cuff, the squeezing of the bulb to inflate the cuff. Those aren't interesting. The ones that start at about 10 seconds, though, those are due to my pulse. And so those are interesting. And we can also do the low pass. So if we go back to the terminal and we look not at column 3, but at column 4, now we have the fluctuations removed. And this is just what is the average pressure in this region. Removing all the high frequency stuff, looking just at the low frequency stuff, the stuff that was eliminated before. For the bandpass, this is the part that's interesting. So how does this thing work? Well, we look for the places where the pulsing due to the pulse gets big and gets small again. And where it first starts, that's where we get the systolic pressure. Where it ends, that's where we get the diastolic pressure. Now the trouble is when you look at this with a cuff like this, it doesn't have as clear a starting and ending point as the auditory method where you're listening to the turbulent flow. And so different manufacturers have come up with somewhat different heuristics for trying to figure out, well, where is it starting and where is it stopping to get consistent measurements for systolic and diastolic pressure. And there's some heuristics for doing that in the textbook. I'm not going to try going through them here. But it's basically what fraction of the peak fluctuation do you see? So when the fraction of fluctuation gets big enough, that's where the systolic pressure is, and when it shrinks again, getting small enough again, that's where it's the diastolic pressure. And how big is big enough? I give some heuristics in the book that I got from one author, but every manufacturer of the home blood pressure meters seems to have picked their own way of calibrating that, and so it's not a well-defined standard. But basically, this is what you need to do for this lab: is get your pressure sensor working, get your amplifier working, and then you're going to have to provide the output here not in volts as I've done here. I mean, the raw output from the amplifier is in volts. That is useless to a doctor. A doctor has no idea what blood pressure 3 volts corresponds to. Is that dangerously high? Is it dangerously low? They're not going to know. Depends on all sorts of details. So you're going to have to convert it back into one they will understand. And that is millimeters of mercury. A very strange unit that's basically only used for barometric pressure and blood pressure. Okay, so millimeters of mercury, one thing is you should know that normal blood pressure is going to be something like 120/60. So if you're getting, hey, I'm seeing systolic pressure of 300, you probably screwed up. That's probably not the right computation. For one thing, this mechanical gauge, which you can have hooked up to your cuff while you're doing your measurement, so you have a backup thing and saying, gee, I pumped it up to 180, and so when you're looking on your plot, if it doesn't go up to 180 when you did it, again, it's a sanity check. Did you get your computations right? Because what you have to do is to take the output voltage subtract off what voltage you would get at zero pressure, and then multiply by a scaling factor that takes into account the gain of your amplifier, the sensitivity of your pressure sensor, and then the conversion from pascals or kilopascals, which is what the pressure sensor is calibrated in, to millimeters of mercury. So you've got several multiplications going on there. The conversion between the different types of units, the sensitivity of the pressure sensor, the gain of the amplifier, and you've got to basically undo that multiplication in order to get back from the voltage you've got to the pressure in the units that the doctor will understand. So that's really all there is to this lab, is building your amplifier, making the measurements of your blood pressure, and then trying to interpret the pulsing blood pressure graph that you get in terms of what's the systolic and diastolic pressure. You can also get the heart rate, the pulse rate, from that, because you've got a bunch of fluctuations that correspond to the pulses. You can count how many pulses do you get in a minute. Well, except if you don't want to run for a whole minute. So what you want to do is to look at how much time does exactly 10 pulses take, and that you divide 10 by that time. That gives you how many pulses you get per second, multiply 60, and you've got beats per minute. And you really want to do a precise number of periods of your pulse rather than a precise time, because it's very easy to measure time, but it's hard to estimate, well, is that 10.3 pulses, 10.2 pulses? Very hard to tell that. But if you've got exactly 10 pulses from corresponding points on the waveform, then you can say, well, if that takes 10.3 seconds, that's an easy measurement to make. You can just look for where they occur on the x-axis. So measure an integer number of pulses rather than a fixed period of time when you're trying to estimate what the pulse rate is. Okay, I think that's enough for this demo.